Today's topic is nearest neighbor classifier. Nearest neighbor classifier is one of the simplest classifier and very easy to understand. Let's get started. Euclidean distance for 2D. The distance between 2 points x1, y1 and x2, y2 is x1 minus x2 the whole square plus y1 minus y2 the whole square to the power of 0.5. Suppose you want to calculate the Euclidean distance between minus 3, 5 and 7, minus 1. You want to find the Euclidean distance between these 2 points. Over here, x1 is equals to minus 3, x2 is equals to 7, y1 is equals to 5, y2 is equals to minus 1. We plug in these values in this formula and this formula gives us the distance to be 11.66. Nearest neighbor classifier. Let X be the space of all possible patterns for some classification problem, which means that we have some kind of classification problem and all the possible patterns of this classification problem belong to a space called X. Let F be a distance function defined in X. F assigns a distance to every pair v1, v2 of objects in X. So we're going to define some kind of a distance function F, so this distance function is going to return us the distance for every pair of objects that is in X. What are the possible examples of such kind of distance function F? One of the possible distance function F can be is L2 distance, which is also called as Euclidean distance that we saw in the first slide. So this is the generalized formula for Euclidean distance. So L2 of v1, v2, the distance between v1, v2 is this formula over here, where I goes from value of 1 till d dimension. So suppose you have as 5-dimensional space, then I will go from 1 to 5. And another possible distance function that we can use is Manhattan distance. This is the formula for Manhattan distance. Now let us consider x1, x2, x and b training examples. The nearest neighbor classifier classifies any pattern v as follows. So how will a nearest neighbor classify a test pattern v when we have the training examples as x1, x2, xn? So the first step, find the training example c of v that is nearest neighbor of v, which means it has the shortest distance to v among all training data. So the first step is that we are going to find a training example which is nearest to v, which has the shortest distance to v among all the other training data. So this formula over here says that point above. C of v is equals to minimum of all the distances of v from every x. So we're going to return the class label of this C of v, which means in short each test pattern v is assigned the class of its nearest neighbor in training data. So if you didn't understand anything from the previous slides, then we are going to go through few examples so that you have a clear understanding of how nearest neighbor works. So suppose that we have a classification problem where we have three classes: red, green, yellow, and it's a two-dimensional vector. The patterns are two-dimensional vectors, and this is our training data. Okay, suppose we have a test pattern v shown in black. This is the test pattern. So how is v classified by the nearest neighbor classifier? So how does nearest neighbor classifier classify this black test pattern? So we have to classify this test pattern v to be either red, green, or yellow. So let's go back and let's see the step 1. We're gonna find the training example that is nearest neighbor of v. For that we need to compute the distance of v from every training example. So we're gonna compute the distance from this test pattern, the distance of this from this pattern, from every training example that we have over here, and the shortest distance the test pattern v has from all the training examples is this pattern over here. So this is the nearest neighbor to this test pattern v, as you can see pointed out by an arrow. So therefore v is classified as red because the class of nearest neighbor of v is red. Now if the test pattern v is over here, then the nearest neighbor to test pattern v is this pattern over here, which is yellow. So we're going to give the test pattern v as yellow. Therefore v is classified as yellow. Now over here the nearest neighbor is this green pattern, so we're going to give this therefore V is classified as green. Okay, this is a very interesting case over here, K-Nearest Neighbor Classifier. Now over here, the test pattern is nearest to this red pattern, but if you observe clearly, then it is surrounded by yellow patterns. This test pattern is just surrounded by one red pattern, but most of the pattern it is surrounded by is yellow. So what if we consider 3 nearest neighbor instead of 1 nearest neighbor? So the 3 nearest neighbor to this black pattern is, to this test pattern V, is yellow, 2 yellow and 1 red. And then we are going to return yellow as the class of this test pattern V, because the 3 nearest neighbor has yellow patterns more than red patterns, so we're gonna return yellow as the class of this test pattern V. So what does this tell you? This tells us that if we increase our neighbor, then it can help us avoid mistakes due to noisy data. It can improve our classification accuracy. So the value of k is something that we choose, and so it's good to choose odd values of k, like 3, 5 and 7, and check whatever k value gives you the best accuracy, just go with it. Normalizing dimensions. This is very important. Okay, suppose that your test patterns are two-dimensional vectors representing stars. Your test patterns are stars. Your first dimension is surface temperature measured in Fahrenheit, the surface temperature of a star. Your second dimension is mass measured in pounds. Now the surface temperature can vary from 6,000 degrees to 100,000 degrees, and the mass can vary from 10 raised to 29 to 10 raised to 32. Over here, the maximum value that a surface temperature can get is not even nearer to the minimum value that mass has for a particular testing data. So does it make sense to use the Euclidean distance or Manhattan distance here? No, these distances treat both dimensions equally and assume that they are both measured in same units. Applied to these data, the distances would dominated by differences in mass and would mostly ignore the information from surface temperatures. So that's right, that's true, because the value of mass is too high than the value of surface temperature. So obviously the distance of the mass, the dimension mass, will dominate over the distance of the surface temperatures. Okay, which means that we are giving more importance to the distance of the dimension between mass than the surface temperature. So it's very necessary to normalize your data. And if you think that mass is really important, then the surface temperature, then you can use a distance function that gives more importance to few dimensions like Moholy-Nagy distance or other distance functions. So it would make sense to use the Euclidean distance or Manhattan distance if we first normalize dimensions so that they contribute equally to the distance. So how can we do such normalizations? We have two common approaches over here: translate and scale each dimension so that its minimum value is 0 and its maximum value is 1. So we can do this by dividing the every value of that dimension with the possible maximum value that dimension can have. So in that way we can scale the value of each dimension between 0 and 1. Or second approach is translate and scale each dimension so that its mean value is 0 and its standard deviation is 1. So this was it for today. This was all about nearest neighbor classifier, and what all we have learned today, that we are going to write a code on nearest neighbor classifier, and what all we have learned today, we're going to apply it in our code. Okay, so yeah, that's it. Thank you guys, and if you like our videos, then do subscribe to our channel Nerdsup, and don't forget to hit the like button. All right, bye, see you.